If you were to walk into a high-security propulsion laboratory, place a glass beaker on a steel table, and fill it with the liquid known as Jet A1, you would be looking at one of the most deceptive substances in the history of engineering. To the naked eye, it appears underwhelming. It looks like dirty water, perhaps with a faint, straw-colored tint. It smells heavy, oily, and pungent, reminiscent of the kerosene camping lanterns of the early 20th century. But here is the paradox that breaks the intuition of almost everyone who is not a professional chemical engineer. If you were to light a wooden match, let the flame grow to its peak intensity, and then drop that burning match directly into the cup of jet fuel, do you know what would happen? Nothing. There would be no cinematic explosion. There would be no sudden, towering inferno. The match would likely hit the surface of the liquid with a small splash, hiss as it was suffocated, and simply go out. It would drown in the fuel, extinguished as easily as if you had dropped it into a cup of lukewarm tea. This creates a cognitive dissonance. We are conditioned to believe that aviation fuel is a volatile, hair-trigger explosive. We assume that because a modern turbofan engine is the pinnacle of high-performance mechanical violence, the fuel feeding it must be equally aggressive. We imagine it to be far more dangerous and reactive than the gasoline we pump into our family sedans. The reality is the exact opposite. Gasoline is a nervous, erratic chemical. It is desperate to vaporize. It wants to turn into a gas and explode at the slightest provocation. Jet fuel, by contrast, is calm. It is stable. It is chemically heavy. And it is this very reluctance to burn, this stubborn refusal to ignite, that makes it the only liquid capable of carrying 300 human beings across the Atlantic Ocean at 80% of the speed of sound. To understand why we trust our lives to this oily fluid, we have to stop looking at the airplane, and start looking at the carbon atom. When aerospace engineers design a machine to conquer the atmosphere, they are engaged in a permanent war against two invisible tyrants. These tyrants are gravity and drag. Every single gram of mass added to an aircraft is a tax paid to gravity. Every cubic meter of volume added to the fuselage is a tax paid to drag. The engineer's dilemma is that we need an immense amount of energy to push a 300-ton metal tube through the stratosphere, but we have nowhere to put that energy. We cannot use batteries. The energy density of lithium-ion technology is laughable in this context. To power a transoceanic flight with batteries, the battery pack would weigh more than the aircraft itself can lift. We cannot use hydrogen, despite its incredible energy per kilogram. Hydrogen is too light. It is too fluffy. To carry enough hydrogen for a long-haul flight, the fuel tanks would need to be the size of a football stadium. The resulting aircraft would be so voluminous, and create so much aerodynamic drag, that it would likely never leave the ground. We need a middle ground. We need a liquid that is dense. We need a substance that packs the maximum amount of heat energy into the smallest possible physical space. We need a liquid battery that we can pour into the wings. We need kerosene. That is what Jet A1 fuel essentially is. It is a highly refined, strictly regulated variant of kerosene. To understand its power, zoom in to the molecular level. Your car runs on gasoline, which is composed of short, light chains of carbon atoms. A typical molecule of gasoline might be a chain of 7 to 11 carbon atoms. These short chains are light and flighty. They break apart easily. Jet fuel is built for heavy lifting. It is made of massive hydrocarbon molecules, long chains of 10 to 16 carbon atoms locked together. This difference in molecular weight changes the fundamental physics of the fluid. Because the molecules are heavier and longer, they tangle together like strands of wet spaghetti. They attract each other with powerful intermolecular magnetic attractions known as van der Waals forces. These forces glue the liquid together, making it thicker, oilier, and much harder to vaporize than gasoline. In the world of thermodynamics, we measure this reluctance to burn using a metric called the flash point. The flash point is the lowest temperature at which a liquid gives off enough vapor to ignite in the air. Gasoline has a flash point of -40 degrees Celsius. That means that even in the freezing dead of an Antarctic winter, a pool of gasoline is emitting enough explosive vapor to ignite with a single spark. It is dangerous. It is volatile. It is always ready to blow. Jet fuel, however, has a minimum flash point of 38 degrees Celsius, or 100 degrees Fahrenheit. On a standard day, jet fuel does not want to turn into a gas. It wants to stay a liquid. This is a critical safety feature designed into the physics of the fluid itself. When a fuel truck is pumping thousands of gallons of Jet A1 into the wing of an airliner while passengers are boarding just a few meters away, we cannot have explosive vapors drifting across the tarmac. We need a fuel that stays liquid, safe, and inert, right up until the moment we force it to burn. But this safety feature creates a nightmare for the engine designer. If the fuel does not want to burn, how do we release the megawatts of power required to spin the turbine? The answer lies in a process of extreme mechanical violence known as atomization. Follow the journey of a single droplet of Jet A1 as it leaves the wing tank. It is sucked into a high-pressure fuel pump. This is not a simple swimming pool pump, it is a precision hydraulic machine that raises the pressure of the fluid to over 1,000 pounds per square inch. At this stage, the fuel is no longer just a fluid, it is a hydraulic ram. It is compressed energy, waiting for release. It is pushed through a steel manifold and delivered to the fuel injectors, which sit at the very heart of the engine's combustion chamber. Here, the engineering must overcome the chemistry. Since the fuel will not vaporize easily on its own, we have to rip it apart. The fuel nozzle is not just a shower head. It is a precision machine vortex generator. As the fuel exits the nozzle, it is hit by a blast of high-pressure air from the engine's compressor. This air is often swirled in counter-rotating directions to create maximum turbulence. This shearing force tears the solid stream of liquid into ribbon-like ligaments. Then, the turbulence shatters those ligaments into microscopic droplets. We are talking about droplets measured in microns, fractions of the width of a human hair. By shattering the liquid, we increase the surface area of the fuel millions of times over in the blink of an eye. Suddenly, that stable, lazy liquid is transformed into a mist so fine it behaves like a gas. Now, and only now, can we light the fire. Inside the combustion chamber, the environment is apocalyptic. The temperature soars to over 2,000 degrees Celsius. This is hot enough to melt the superalloy walls of the chamber itself. The only reason the engine does not melt into a pile of slag is because of the fuel's secondary job. Before the fuel is sprayed into the fire, it is often routed through heat exchangers to cool the engine oil. It acts as a liquid coolant, absorbing the waste heat of the mechanical systems. It washes away the thermal energy, preheating itself in the process, preparing its own molecules for the final combustion event. But while the engine fights the heat, the fuel in the wings must fight a hidden enemy in the sky. An enemy that tries to kill the engine not with fire, but with ice. When a modern aircraft cruises at an altitude of 35,000 feet, the outside air temperature drops to -55 degrees Celsius. The massive wings of the plane, which serve as the main fuel tanks, are essentially giant aluminum radiators. They sit in this sub-zero airstream for hours, cold-soaking the fuel. Remember those long, heavy chains of carbon atoms we discussed? The ones that give jet fuel its incredible energy density. When they get cold, they behave badly. The paraffin and wax components inherent in the crude oil begin to crystallize. Microscopic solids start to form in the liquid, like wax congealing in a cooling candle. If these wax crystals grow large enough, they will link together. They will form a slush that clogs the fuel filters, starving the engines of energy and turning the plane into a 300-ton glider. To fight this, the chemistry of Jet A1 is strictly regulated. Refineries must carefully control the freezing point, ensuring the fuel stays liquid down to -47 degrees Celsius. But even that is sometimes not enough. On polar routes, pilots must monitor fuel temperature obsessively. If it drops too low, they must descend to warmer air or increase speed to generate friction heat on the wings. But the cold is not the only threat lurking in the tanks. There is a biological menace. Jet fuel requires chemical additives, specifically anti-icing agents, that hunt down water molecules suspended in the fuel. You see, water is the arch nemesis of jet fuel. Water is everywhere. It condenses from the humid air into the fuel tanks as the plane descends. Because water is heavier than fuel, it sinks to the bottom of the tank, pooling in the lowest sumps. If that water freezes, it forms solid ice blocks that can destroy fuel pumps. But even worse, if the water sits at the bottom of the tank in warm conditions, it becomes a breeding ground for life. Yes, life. There is a specific fungus, a biological organism known as Formicomys resin, that has evolved to feed on the hydrocarbons in jet fuel. These microbes live in the microscopic interface between the water layer and the fuel layer. They eat the fuel, and in return, they excrete a thick, acidic sludge. This biological slime is corrosive. It eats into the aluminum structure of the wing tanks, causing pitting and structural damage from the inside out. It is a biological attack on an industrial machine. Therefore, jet fuel is laced with biocides and constantly filtered to keep it sterile and dry. We are not just fueling a machine, we are maintaining a sterile environment. Let us go deeper into the combustion event itself. The goal is to release the energy stored in the carbon-hydrogen bonds. When the fuel burns, it is an oxidation reaction. We are breaking the hydrocarbon chains and snapping them onto oxygen atoms. The result is carbon dioxide, water vapor, and a tremendous release of heat. But the speed of this reaction is critical. If the fuel burns too fast, we get a detonation. This creates a supersonic shockwave that hammers the engine blades like a sledgehammer, causing catastrophic structural failure. If it burns too slow, the flame shoots out the back of the turbine, wasting energy and melting the tail cone. The flame front inside a jet engine must remain stationary. Imagine trying to keep a candle lit while holding it out the window of a car driving at hurricane speeds. The air is rushing through the engine at hundreds of miles per hour. The flame wants to blow out. To prevent this, the combustor is designed with aerodynamic recirculation zones. It creates a low-pressure eddy, a swirling back flow of air that anchors the flame in place. The fuel must be chemically tuned to burn with a specific flame speed that matches these aerodynamics. If the refinery leaves too many aromatics in the blend, which are ring-shaped carbon molecules, the fuel will burn with a smoky, luminous flame. This acts like a radiator, dumping radiant heat into the metal walls of the combustor, overheating the liner. We want a lean, blue flame, not a bright yellow soot-filled fire. So, the content of aromatics is strictly capped at 25% by volume. This brings us to the most modern challenge of jet fuel, the thermal stability limit. As engine manufacturers chase higher efficiency, they raise the pressure and temperature of the engine. The fuel sitting in the fuel lines, waiting to be injected, is being cooked. If the fuel gets too hot before it is sprayed, it begins to crack chemically. The carbon chains break down and form solid deposits, a process called coking. Imagine the fuel injector nozzles. The holes in these nozzles are microscopic, drilled with high-precision lasers. If coke deposits form inside these holes, they distort the spray pattern. Instead of a fine, uniform mist, you get a streak of liquid. This streak burns unevenly, creating a localized hot spot on the turbine blades. A single hot spot can burn a hole through a turbine blade in minutes, destroying a $20 million engine. So, the fuel is not just a commodity, it is a structural component of the engine's design. It is a coolant, a lubricant for the pumps, a hydraulic fluid for the actuators, and finally, the energy source. We must also address the sheer scale of consumption, because the numbers are numbing. A large long-haul aircraft like the Airbus A380 can carry over 300,000 liters of fuel. The weight of the fuel alone is significantly heavier than the entire empty aircraft. At the moment of takeoff, the plane is essentially a flying fuel tank with some seats attached to it. The pumps that move this fuel are feats of engineering in themselves. They have to move fuel from the wingtips to the center, keeping the aircraft balanced as the fuel burns off. If the center of gravity shifts too much, the plane becomes aerodynamically unstable and uncontrollable. So, a complex computer system manages a sequence of valves and pumps, shifting tons of liquid around the airframe while you sleep in seat 34F. You are riding on a dynamic, shifting ocean of kerosene. And what about the future? We hear constantly about sustainable aviation fuel, or SAF. This is where the chemistry gets truly fascinating. We are trying to replicate the magic of kerosene without drilling for oil. We take cooking oil, agricultural waste, or even capture carbon directly from the air, and we use massive amounts of energy to force these atoms into the same long-chain hydrocarbon shapes as fossil jet fuel. The challenge is not making it burn. The challenge is making it boring. Remember, the current fleet of aircraft has been designed for 50 years around the specific density, viscosity, and seal swelling properties of standard Jet A1. If we introduce a synthetic fuel that is too pure, we encounter a serious problem. The rubber O-rings and seals in older jet engines rely on the impurities in fossil fuels, specifically the aromatics, to swell up and create a tight seal. If we run pure, synthetic fuel, the seals shrink, and the engine begins to leak fuel. It sounds insane, but the impurities in fossil fuels actually help seal the engine. So, when we make synthetic fuels, we sometimes have to add impurities back in, just to make the fuel behave like the vintage liquid the engines expect. We are trapping lightning in a bottle, trying to mimic a substance that nature spent millions of years cooking. We are taking a liquid that is stable enough to sit in a tank for months, safe enough to be pumped through hot pipes, and yet energetic enough that a single gallon contains enough potential energy to fling a 1-ton weight 30,000 feet into the air. The next time you look up and see a plane streak across the sky, leaving a white contrail behind it, remember what you are seeing. That white trail is water. It is the hydrogen atoms from the fuel, liberated from their carbon chains, bonding with oxygen and freezing instantly in the cold upper atmosphere. It is the ghost of the fuel. It is visible proof of the violent, precise, and miraculous chemistry that just took place inside the engines. We often praise the titanium blades, the carbon fiber wings, and the digital avionics. But the unsung hero of aviation, the lifeblood that makes the defiance of gravity possible, is that straw-colored, smelly, oily liquid that refuses to burn until we force it to. It is a masterpiece of chemical engineering, refined to the edge of perfection. To keep deconstructing the world's most complex systems, stay connected to Gradonics.